Hi, Chris Good here. Here's another video solution to a practice analysis variance problem. This is practice ANOVA problem number 3. And I've done a couple of things in advance to make this video a little bit shorter. The first thing I've done is I've got totals for each one of my columns. And I have done the sums of squares for each treatment. Let's read about what treatments these are. Okay, neuroscience researchers examined the impact of environment on rat development. Rats were randomly assigned to be raised in one of the 4 following test conditions. Impoverished, that's a wire mesh cage housed alone. Standard is in a cage with other rats. Enriched is a cage with other rats and toys. And super enriched is cage with rats and toys changed on a periodic basis. So after 2 months, the rats were tested on a variety of learning measures, including the number of trials to learn a maze to a 3 perfect trial criteria. So fewer trials to learn it means they're smarter, means they're better at it, and other neurological measures, But the data for the maze task is what we're concerned with. Compute the appropriate test for the data provided below. Well, we're going to use the independent groups in ANOVA because these are groups of different rats, and we're going to do all the normal hypothesis testing statistics procedures, starting with the null hypothesis. It's just that the mu for the first group is equal to the mu for the second group. It's equal to the mu, the population mean for the third group, which is equal to the population mean for the fourth group. Sorry, so this is impoverished, standard, enriched, and super enriched, and that's our null hypothesis. So the rest of the statistic is calculated under the assumption that that is true, that we sampled these 4 groups from populations with means that are equal to each other. Step 2 is for a given alpha, and I'm going to use 0.05 just like we have been, find the critical value for f. F is always going to be a one-tailed test. That distribution only has one tail. But in order to look up the critical value for f, we need 2 types of degrees of freedom. The first is the degrees of freedom for the numerator term, which in this case is the between treatments, right? Degrees of freedom. So that's always equal to k, the number of groups you have, minus 1. We have 4 groups, minus 1 is 3 degrees of freedom in the numerator. And the second one is the degrees of freedom within treatments. That is degrees of freedom associated with the term that's going to go in the denominator within treatment's mean square. So within treatment's degrees of freedom is always equal to big N, the number of scores you have. We have 5 scores in each of 4 groups for a total of 20 scores. Minus the number of groups you have. That's the same as adding up all the degrees of freedom in each group, because you take this group minus 1, this number of scores in here minus 1, minus 1, minus 1. It's the same thing as having all these scores minus 1 for each group, minus k. So that's 20 minus 4. We have 16 degrees of freedom for the denominator term. Now, we will go to our F table, and we will look up, here's our F table. What's the critical value for F when we have 3, right, and 16 degrees of freedom? So 3.24 is what I see here as the critical value when alpha is 0.05. F crit 3.24. 3.24. All right. Step 3 then is to compute our test statistics. So what we're going to do is we're going to do the denominator term first, because I've already got our sums of squares for each group. All right. So our sum of squares within treatments is just going to be the sum of all the sums of squares for each treatment, right, which is equal to, and I'm just going to read them right off of here, all right, 49.2 plus 48.8 plus 22.8 plus 14.8. All right, 49.2 and 48.8 and 22.8 and 14.8, that's 37.6. That is our sums of squares within No, that can't be right. I added this wrong. Let's do it one more time. 49.2, 49.2, and 48.8. I think I hit the minus button. And 22.8, and 14.8 should give us 135. There we go. 135.6. If you get that didn't make sense. If you get an answer that doesn't make sense, go back and do it again. All right. That's our sum of squares within treatments. The denominator term is the mean squared within treatments. That's variance, which is always sums of squares over degrees of freedom. Here it's sum of squares within treatments over degrees of freedom within treatments, or 135.6 over 16. I get 8.475. Great. The next thing we need to do is sum of squares between treatments. That's equal to the sum of the t-squares over their respective n's, right? Sorry, try to make squared. Minus g squared over big N. We didn't write down what g was. Let's see what that is really quick. That's the sum of all the t's. So 98 and 84 and 61 and 46 is 289. And our t-squares are 98 squared. We're going to divide that by 5 scores in that group. 84 squared over 5. 61 squared over 5. And 46 squared over 5. Minus our 289 squared over 20, because that's big N. Right? Big N was 20 scores. Okay, so 98 squared is 9604. 84 squared, 84 squared is 7056. 61 squared is 3721. And 46 squared is 2116. 289 squared is 83,521. We'll divide that by 20 in the next step. All right. 9604 divided by 5 is 1920.8. 7056 divided by 5 is 1411.2. 3721 divided by 5 is 744.2. And 2116 divided by 5 is 423.2. We'll subtract 83521 divided by 20, which is 4176.05. So I'm running out of paper here. And we'll add it all up. 1920.8 plus 1411.2 plus 744.2 plus, oops, made a mistake. Try to get 1920.8 plus 1411.2 plus 744.2 plus 423.2. That's 4499.4 minus 4176.05. I get 323.35. That's our sum of squares between treatments. But we want the mean squared between treatments, which is variance. So that's the sum of squares between treatments over the degrees of freedom between treatments. Or or 323.35 divided by 3. That was our degrees of freedom between treatments. So that's 107.78 with the rounding. Now we can finally calculate our test statistic, which is the ratio of the variance between treatments to the variance within treatments, or 107.78 divided by 8.475. $12.72 with the rounding. We'll compare that to the F-crit, which was 3.24, and allow us to reject the null hypothesis. Well, if we reject the null, that means that somewhere among these 4 means, which we haven't actually calculated yet, so we need to calculate these 4 means. In fact, let's do that really quickly. If this t is 98, then 98 divided by 5 is the mean, 19.6. The mean here is 16.8. The mean for the enriched group is 12.2, and the mean for the super enriched group is 9.2. All right. So we know that there exists at least one significant difference between at least 2 of these means, but we don't know what it is. So to find out which differences among these means are significant, we need to do a post-hoc test. And the one that we're learning how to do is Tukey's honestly significant difference. That's equal to this quantity called Q, which is the studentized range statistic, which we're going to look up in a table, times the square root of this entire quantity, MS within treatments, divided by n. Now you can only use Tukey's HSD when the n's are equal in each group. So let's take a look very quickly at the Q table. We do have equal n's in each group, so we can use this. So we're going to look at the Q table that I've got right here in my Evernote and see how to look up the studentized range statistic. So it's kind of like the F table, but you use the number of treatments instead of degrees of freedom. We have 4 different treatments, and the degrees of freedom in the error term was 16. So we'll scroll down here and find that Q in this case is equal to 4.05. So HSD is going to be equal to 4.05 times our mean square within treatments, which remember was 8.475. Right, 8.475. Divided by n, which was 5 in every single group. So 8.475 divided by n is 1.695. So this is going to be 4.05 times the square root of 1.695. We'll square root that. Or 4.05 times 1.30 with rounding. And I get 5.27 with rounding. So HSD means honestly significant differences and difference, and our means here were 19.6, 16.8, 12.2, and 9.2. All right, this is how big a difference between 2 means has to be significant. So the difference between 19.6 and 16.8 is not significant because it's not this big or greater. But the difference between these two, right, 19.6 minus 12.2 is significant because 7.4 is greater than 5.27. Similarly, the difference between 19.6 and 9.2 is significant because that's 10.04, greater than 5.27. We've got a couple more differences we can check out this way. 16.8 minus 12.2 is not a significant difference because that's 4.6, right? Smaller than that. But 16.8 minus 9.2, this difference is significant because 7.6 is greater than 5.27. 0.27. The last one we can consider is this one, 12.2 minus 9.2. That's 3, so that's not a significant difference. So what can we say at the end? Well, there's a significant overall effect of environmental condition on the number of trials that it takes to learn a maze. And post-hoc testing with Tukey's HSD revealed that the super-enriched environment produces significantly better learning than the standard environment or the impoverished environment. The enriched environment produces better learning than the impoverished environment. And those are the only differences that are significant. All right, we'll see you in the next video.